So I decided I want to investigate the origin of the H5 clades. Now, because I've got data to do with the origin of each one of the different H5 clades, I can construct a tree using Beast, which will allow me to incorporate this date information. A traditional phylogenetic tree doesn't include the dates, it just includes the calculated distances between the sequences. But if you know when they've been collected, then you can use this extra information as well. Now, to do that, the first thing I need to do is have a good alignment. Now, for the H5s, because they're all very similar to each other and alignment is not terribly difficult, so you can see here that there's lots of stars. I've got the start code on my, as you saw, was set. Everything's pretty good. And I've got dates for each one of the sequences. I've taken the oldest one of each of the sequences. The two that are unusual are the American non-GSGD and the Eurasian non-GSGD. So these are the non-highly pathogenic ones that have been around for the longest period of time. The pathogenic ones originated after the GSGD, which is the goose in Guangdong, in 1996-1997. So prior to that, only those bottom two categories, which you can see are the most different ones, occurred. There is an insertion that occurs there between one particular clade and the rest. And there's also a sizable deletion, which you can find in the non-GD sequences, as well as one other. But in general, the alignment is pretty well done. You could use cast out omega, you can use muscle, it doesn't really matter. You'll get a pretty effective alignment. The end's very jagged, and it's probably a good idea to remove this. So you have different lengths of sequences. These are non-coding parts of the sequence, so they're past the stop codons. So they're not really that important. So once you've got a good alignment and you've edited it and you're happy with it, I can export this one, and I've just overwritten the original file because all I've done is done a bit of truncation. So that's everything done. So I could create a normal phylogeny using Mega, but because I want to include the dates, I'm going to use Beast. So the first thing is to use Beauty, which you use that to read in the sequence files. So you import the alignment, and that's my first set of data. It's a nucleotide sequence, that's all fine, and that's good. So next thing I want to do is extract the tip dates for those 28 sequences. It's a small number, I could do them by hand, but I'd still sooner do it automatically. I'm not going to set it to be dates by days, I'm going to set it to be dates by years, because there's quite a wide range of years for these particular sequences, and if I do it by days, I'm going to end up with thousands of days in my time slicing, and it makes more sense just to use years. So I'm going to use tip dates. So what I need to do is automatically get it to load them, and the format is year, then month and day, which agrees with what you can see in the headers for each of the files. I'm going to automatically pick them, and I'm going to use the split character, which is the vertical straight line. So I put that as the split character, and I want the second set of data after that split, because that happens to be the years, and then OK, and hopefully it's going to pick them correctly. So the most recent sequence is the one set as 0, and then all of the others have got fractions of a year. So they're decimal places, it doesn't really matter, and you can just look and check that they're about right. So it's 13 years and 6 years and 42 years or whatever else, 1.2 years. So all related to the latest sequence, which was collected in 2009. For gamma categories, we want 5. For proportion invariant, I don't know. It's definitely more than 0. 0.1 is a reasonable guess. Now, as there's not a massive amount of sequences, you can't use GTR are, so I'm probably going to use the best one I can do, which is TN93. This just has two parameters, two kappa parameters, so I'll let the program work those out. Going to use a strict clock. With priors I can't use Yule, I have to use a coalescent model because otherwise the tips are ignored. Tip models requires you to use a coalescent to do the modelling. Any other model is not compatible with that. Well, there's skyline plots which also use the tip dates. So these are the two different ways of doing it. All the other parameters, I could make more sophisticated mathematical guesses, but I'm not going to. And for MC, I'm going to leave the number of iterations as set. So I save that file. I give it a name which is sensible. So usually it's going to be the same as the alignment file, but you just get rid of the FAS at the end and align muscle. So I'm just going to have that as an XML file, which is the file that I'm going to put into Beast. So now I run Beast. So I input that file that I created with Beauty. Once I find it, so I have to go through my file system to downloads. And there's my Beauty file. Everything else is all right. I'm going to run it on 2 threads and 2 instances to run it a bit faster, but there's not many sequences, so this should run pretty fast anyway. So when I press run, you can see it's speeding through and it's taking 1 minute, 14 seconds, 12, 11. It's taking about a minute to do 1 million samples. That's really fast compared to the usual sort of speed that you get for running these processes. Now I truncated this and just ran it till the end. So there it is after it's completed, and I can close Beast and then I can start looking at the output. So first I use Tracer to check that the output has converged. So you load the log file into Tracer. Once the log file has been loaded into Tracer, then you get the graphs of the output. Now the first thing you want to look at is the table and the ESSs, and you don't want any of them in red or yellow, you want them all in black, and they are. I can look at the clock rate and the population size. These two things are intimately connected with each other. When you multiply the two together, it tells you the number of changes that you're going to have per year, because it depends on population size and that clock rate. And it also tells me the tree height. So the tree height, which is 74.33, is how many years ago H5 originated. So remember, it's dated from 2009. So it's on average about 70, let's say 75 years in front of 2009. So that'd be about 1934. But if I go to the tree height, I can look, and the confidence interval actually goes between those two values. So between 80 years and 69 years. So somewhere in that period, H5 originated. So that's somewhere between, in the interwar period, between the First and Second World War. Flu tends to be turned up where there's lots of human activity, like in war. So H1 is believed to have started, so the Spanish flu is believed to have started in France, in the trenches, and that was its point of origin. So any time you've got big displacements of humans into non-usual environments, you're likely to get a virus go from a different species into humans. So that is consistent with H5 arising during the upheavals that happen between the two wars. So potentially it could have arisen just after the First World War, when there was still problems with other things like the Russian Civil War, or it could be up until the later disturbances that we got in the 1930s.